I'm Kirk Harnack. On This Week in Radio Tech, I'm at Riga, Latvia. Chris Tobin, Tom Ray, and Chris Tarr join me for a look at EM testing and a quick radio station tour. On This Week in Radio Tech, next.
Netcasts you love.
From people you trust.
This is TWiRT.
Bandwidth for This Week in Radio Tech is brought to you by CacheFly at CACHEFLY.com.
This is This Week in Radio Tech, episode 117, recorded February 22nd, 2012. 4 kilovolts and counting. This Week in Radio Tech is brought to you by the Telos Alliance and the astonishingly gorgeous Now catalog, featuring color pictures, diagrams, techie specs, and many words of modern radio wisdom. Telos will mail it to you free, and you can download the PDF. Get yours at telosalliance.com/now. Hey, it's time for This Week in Radio Tech. I'm Kirk Harnack, your host. Thanks for joining us. This is the show where we talk about, radio technology, what's happening this week, and we also talk about, fundamentals of engineering and radio technology, audio technology, RF technology, things that, that put a signal into the homes of literally billions of people around the world, and certainly hundreds of millions in the U.S. So thanks for joining us. Our show is brought to you by Axia Audio on the web at axiaaudio.com. Let's bring in our co-host here. Let's start in Mukwonago, Wisconsin today and talk to Chris Tarr. Hey, Chris, how are you?
I'm doing fine, thank you, and welcome back to the U.S. from Latvia, where you said 3 a.m. Not quite that early in the morning here. I don't know if I could make that happen the way you are. You are twice the man that I am. I am the Director of Engineering for Intercom's radio stations in Madison and Milwaukee, also a contributing writer to Radio Guide magazine, and run the website, the virtual engineer at broadcastengineering.info, among many other things.
Hey, Chris, speaking of your writing that you've done in Radio Guide, you put some really practical knowledge into your articles in Radio Guide, and I enjoy reading them. Are those available only at the Radio Guide website, or are they also reprinted somewhere else like your website?
You can find them at radioguide.com. I also, a lot of the older articles I have archived on my site, which you can get to at broadcastdoc.com.
Broadcastdoc, as in DOC, as in doctor.com. All right. Well, I encourage everyone to bookmark that to radioguide.com. It's a great site for practical information, isn't it? All right, let's move along to the Hudson Valley of New York. Tom Ray is the chief engineer for WOR, and he's also the VP of engineering and IT and something or other for Buckley Broadcasting. Hey, Tom.
And who was busy spending the day today celebrating the birthday of a grand old gal. Today is WOR's birthday, 90 years young.
Really? 90? Holy cow.
Yep. We went on the air February 22nd, 1922 from Bamberger's department store with a whopping 500 watts.
You have radio back then? How nascent was radio at that time?
Not very. There were only 2 stations in New York at the time. WJZ, which became WABC, and WOR. We are the only station in New York to retain our 3-letter call sign. The only station that was on the air on Christmas Day, because, of course, being Bamberger's department store, they had these new things called radios to sell, and they wanted to make sure when people opened them up on Christmas morning, they had something to listen to. Louis Bamberger, who owned Bamberger's department store, actually has the distinction of having the pretty much the first boneheaded general manager move in radio history. He on New Year's Day, they said, you know what? Radios are sold out. Turn the license in.
So, Tom, were you still the chief engineer back then when they launched?
I'm not quite that old, but you think back to that time, and it probably was a lot of fun. It probably really was, through the golden age of radio. And actually, I've got a quick pop quiz for you after we introduce the other guys.
Well, let's check in with Tobin, the best dressed engineer in radio from Manhattan, New York. Hey, Chris.
Hello, everyone. It's a wonderful day here in Manhattan. I'm Chris Tobin. I'm president of MusicCam USA. We do a little codec work and IP and video. And I'm also enjoying a lot of talking to folks who've been emailing me for advice on a few things for broadcast engineering, which has been fun, without the need of worrying about who to talk to and making clearances. It's been fun. So keep those emails coming in, and the checks are welcomely appreciated.
All right. Well, thanks, Chris, for being here. Now, I understand you've got some show and tell for us later on in the show, right?
Yeah, if you like. I mean, it's kind of, it's just a very simple thing. Most people recognize the green circuit design and stuff. But yeah, more than happy to talk about it. It'll be fun since you're doing EM testing and stuff.
I want to know what's on that board. We'll yeah. In fact, that'd be a good dovetail in the EM testing thing. All right, what's the quiz, Tom Ray? What's up?
Well, it's in regards to WR. Actually, I had two questions here, and this is actually they're both actually quite interesting. If you don't know, WOR was one of the forces behind the formation of the Mutual Radio Network, with programs like The Shadow and Superman and The Lone Ranger. The Shadow actually was produced at WR in New York. But here's the question. There was another radio network, and their fledgling broadcast, their first broadcast, was produced by WOR in New York City. And as a quick side note, because WR didn't have a place for their control room, they built it in the men's room. What network was that?
Oh, gosh.
Dumont?
Nope.
Dumont. NBC?
Nope.
Men's network.
It was the CBS radio network, because there was no WCBS at the time.
Oh, that's right.
Now, next question. Next question, and I actually found this in a book. It's called The Great American Broadcast by, last name is Malton, and I can never remember the guy's first name. Anyway, in the golden age of radio in the mid-1930s, it was very common for a bit part actor in a radio drama or a radio show to have literally one line in a radio show. And sometimes they had one line in 3 different shows on 3 different networks on the same night, all very close to each other. And CBS and NBC were uptown, which, NBC is up at the 30 Rockefeller Center, which is up at 49th and 50th Streets, pretty much where they are today. CBS was around the corner, so a bit part actor going from CBS to NBC and vice versa wasn't really a problem. Where the problem came in was WOR was down in Times Square. So how did the actors get from uptown or deeper midtown, if you will, down to Times Square to literally walk in, be handed a script, read one line, and walk back out?
So what was their mode of transportation?
Yes, and the subway, while it was in existence, is not the mode.
Streetcar, Fifth Avenue trolley?
Nope.
Pneumatic tubes like at the bank.
I wish. No, they hired off-duty ambulances.
What?
To drive them up and downtown.
Meat wagons.
With the lights flashing and the whole bit.
Oh, jeez.
Fine.
So that's my old radio quiz for tonight.
The days of yore.
I like the second one better, but I like the answer, the ambulances. Oh, my goodness. Radio was very... Wow. So, I ran radio drama. These guys are reading in dramas. This wasn't, delivering the news.
Right, and some of these guys literally would show up, walk in the door, be handed a script, walk up to the microphone, read the line, walk out, walk towards the door, hand the script to somebody, and walk back out, getting back in the ambulance and go back uptown.
So
That's
good
a
April
professional.
Fool's joke. Mr. whoever it might be, Mr. Jones, we're sorry the ambulance is not available. We've got you a hearse.
Can you imagine?
Actually,
In
I believe
other words-
I believe the great late Don LaFontaine probably worked that way too. Would walk in, take our limo, walk in, read one line, hand the script back, walk out, and collect a check. I'm sure it's how he operated as well.
Hey, there's got to be worse ways to make a living.
Well, guys, let's jump right into this. For those of you joining us late, I happen to be out of the country, out of the U.S., where I usually am. I'm in Riga, Latvia, and it's my job that has taken me here for the week. Riga was a big technology center for the former Soviet Union. And in fact, I guess the short version of the story is, and I hope I get this right, was when the Soviet Union took over the Baltic states, Estonia, Latvia, and Lithuania, turned out that Latvia, Riga Latvia specifically, was already a technology center. And so during the Soviet days, the several decades of the Soviet Union, turned out Riga was the center for a lot of building of speakers, radios, and telephony. In fact, they built phone switches here in Riga, and they taught. They had a lot of engineering courses at the University of Riga about telephony, and this was where it all happened. Riga was also a pretty popular place for the elite, the Russian elite, to come to, because about 15 miles away from here, I guess it's 23 kilometers, there's a town called Jurmala, and it has a beach that's on the, I guess it's called the Gulf of Riga, which is just off of the Baltic Sea. And this beach is absolutely glorious. Just a beautiful, for being this far north as Riga is, there are some weeks in the summer where it's plenty warm to go swimming and frolicking on the beach, and you can walk way out into the Gulf here and really enjoy the day with the family, or guys and gals looking at each other on the beach. There's also a lot of spendy homes owned by mostly Russians in Jurmala. Well. So it was a popular place to come. Indeed, there were flights from Moscow to Riga quite often, bringing people on vacation and such, and business too. Well, so anyway, Riga is kind of a technology center. It was during the Soviet days, and it still is now that the Soviet Union isn't here, that it's an independent nation. This became very interesting for my friend and boss, the founder of Telos, Steve Church. He was looking around for places to find clever people to write software and incorporate other technologies in the Telos product line. And so he found Riga and befriended a number of people here. And I got to reacquaint myself with some of those technicians and software code writers and researchers today at a couple of locations at the University of Riga. Well, one of the places that I got to visit was really interesting. We're going to roll some video here in just a minute, about a 5-minute video on this trip. But at the University of Riga, in the electronics and telecom department, they have constructed an EM testing lab, electromagnetic testing lab, and this is where they do certification testing for various manufacturers, so that they can make sure their gear is safe, that it's not putting out too much stuff, that it's also immune to being shocked. We witnessed today some guys taking a probe first at 4 kilovolts and then at 10 kilovolts and probing around the top of some new equipment that we're building. So that was pretty interesting and the equipment didn't flinch. I'm told the first test some weeks ago, it did flinch. And so that got fixed. That was very interesting. We have some video we'll roll of that. And then there's I don't know if the right word for this is an anechoic chamber, but there is this chamber, and it's totally sealed. I mean, it's a Faraday cage, totally sealed from any RF. Your cell phone will not work in this room when the door is shut, and neither would anything else that depends on radio waves getting in or out. The room is just totally sealed up with fiber optic cables going in and out through some small holes. The doors even have finger stock in the doors on 2 edges as the door closes, so the room is sealed up tight, and it has all these those pyramidal cones all over the walls, and then it has an area where you set the equipment and plug it in to power, and then it has a calibrated antenna that is pointed at the equipment, and we turn the equipment on, shut the door, and with a very expensive and sensitive spectrum analyzer from a company called Roden Schwartz, we read the signal that emanates from this equipment. And oftentimes it's the cables, so you end up putting ferrite chokes on the cables. Well, Tell you what, let's go around here. Chris, Tom, or Chris, have any of you ever been involved with this kind of testing? Chris Tobin, I suppose that if you haven't yet, you soon will be with your position at MusicCam.
Yeah, actually, I have in the past a couple of times had a chance to visit the UL labs on Long Island, and I was at a facility. Where was it? About 10 years ago with GE, doing similar testing, and it was a demonstration. It was for an engineering society demonstration, but it's pretty wild. Yeah, you go into those RF tight rooms, and it's weird. And it's even stranger when they build a room that's a floating room for acoustic purposes as well for the testing that they do. This place I went to was both acoustic, RF, light. It was like guaranteed the stuff they did there was not just for commercial business, but those other people with those 3-letter acronyms.
Yeah, okay. Chris Tarr, you ever been to a place like this?
No, we ain't got nothing fancy like that out here.
Actually, how about you, Tom? Have you been involved in testing like this?
No, but I have been down in the New York City subway, which is kind of similar. No.
Yeah, absolutely.
Today at this lab, we were testing just a new version of a product that the company I work for is working on. And so hey, Burke, you ready to roll that video? This is the EM testing video.
Sure.
You got it? All right, let's. In February, Riga Technical University, the electronics and telecommunications facilities they have there. This is where they house the Latvian Electronic Equipment Testing Center. This is a project between the University of Riga and the European Union. Here's some equipment under test. This is on audio console. And here they're probing it. They're actually touching the metal parts, probing it with 4 kilovolts at a time. Passed that test okay. This is a test where they actually touched plastic parts with 10 kilovolts. So that probe there is kind of like a stun gun. It has a 10 kilovolts potential on its metal tip there, and they're seeing if it causes.
There is what 8 kilovolts on the probe.
That's it. It said 8. It was actually up to 10 kilovolts. They have to touch buttons over and over again and see if it causes any problem at all when they discharge that or make that 10 kilovolts available there. Next, we moved over to the chamber, the EM chamber. We're going to put the equipment in, turn it on, and point a calibrated antenna at it to read whatever RF products are coming out of the equipment. These are usually caused by clock circuits and switching circuits, especially in CPU-based and DSP-based electronic circuits. And so they're setting the gear up, and they're just about to turn it on. That table that they're setting it up upon actually stands on a turntable. You can barely see it in the floor. The whole floor is able to turn. The testing that they were doing today was not for final certification. It was just a preliminary test to see, okay, what else about this equipment do we need to take care of? So there's the antenna. Looks like a very specialized, some kind of log periodic antenna. It's accurate over a very wide frequency range, or at least its accuracy is known, its calibration is known. And it connects to a Rohde & Schwarz spectrum analyzer back in the testing room. They can move that antenna up and down on that stand as necessary. There you go. There's the antenna pointing at the equipment that's going to be under test in just a few minutes. We've got to shut the door, leave the room. And when we shut this door, that room is entirely sealed off. You can't hear a radio station, or your cell phone certainly doesn't work in that room. By the way, that's the test equipment room. It also closes up to keep anything out. And there's the seal on the door. You see, it's a very, very good RF radiomagnetic shield with all that finger stock around there. Okay, so here's the computer gear that runs the test equipment. The left-hand screen is talking to a Rohde & Schwarz spectrum analyzer that has a bunch of automatic routines built into it. And the screen in the middle there is a camera back to the room. If they were rotating the table on the turntable, then they could see it rotate. And they can also see which polarization the antenna is set to. There's a still photograph of the Rohde & Schwarz spectrum analyzer and a lot of equipment that is associated with it. And here the test goes underway. Today's tests were checking for any emitted radiations between 30 megahertz and 1 gigahertz. So it's going to and the receive bandwidth of the spectrum analyzer, the resolution bandwidth of the spectrum analyzer. These are all fixed items for the test. They know the standards set by the EU for later CE certification. They know what these are, and they're all programmed in the Roden Schwartz. So here's the computer output, or what it's displaying, the data that comes from the Roden Schwartz spectrum analyzer. And you can see the red line across the top there, that is the don't exceed line for a certain class of certification. After they got done with the first round of tests, they went and rearranged the equipment so as to see, okay, is the spikes that we're getting, is it from one piece of gear or from the cable or from the other piece of gear? And so they're just rearranging the test to get some idea, okay, where do we have to go do the work to reduce the electromagnetic radiation spikes in a few areas. And after hiding one of the pieces of gear from the antenna, well, the spectra is down considerably in most areas, although there still are a spike or two above the red line over on the left. So here's the remote rotation of the antenna. They can turn it from vertical to horizontal polarization and test the gear right there. And they're going to run the whole series of tests over again. Once the test is run, the computer actually identifies the places that the peaks that may be over the line and goes and retests those areas with a narrower resolution bandwidth to see if it'll pass the second time. So there we go. That was at the Riga Technical University Electronic and Telecommunications Facility. And almost all those guys speak English. Pretty amazing, which is good because I know like 2 words in Latvian. Guys, let's talk about why is it so important that electronic equipment that you can buy, for sale gear, meets some kind of standards for emission radiation. I guess first of all we want to say, why does this gear put radiation out? Hey, on some of the other shows on the TWiRT network, I hear Leo and other hosts and guests talking about things like using cell phones on airplanes. Hey, why can't we use our cell phone on an airplane? And some of it's political, some of it's convenience, some of it's they don't want the cell phone flying around should they need to bring the plane to a stop during taxi real fast. But part of the idea of the reason is because it's possible for cell phones or any electronic device to put out just a little bit of signal on the same frequency that either the GPS antenna on the top of the plane or the VOR VHF antenna on the bottom of the plane is trying to pick something up. It's important that things not interfere with each other. Chris, why don't you comment on gear generating RF radiation? It's just a computer. Why does it make RF?
Oh, okay. Well, let's see. Let's think about what's inside of a computer. You have oscillators. You have a microprocessor running at various frequencies as high as, 2 gigahertz. These frequencies are technically RF in nature, just like, let's say an AM/FM radio. You have a local oscillator. You have an intermediate frequency. Those are oscillators that create, 455 kilohertz, 10.7 megahertz. You have images that come out of a radio. So if you wanted to tune across the dial and find out who's listening to what radio station in your vicinity, you could listen by hearing the dropouts from the image from the radio that's leaking. So everything emits a signal of some type. So now the question is, do you care? Is it important to life safety in the case of an airplane? And just in general, will you make money in business if your stuff is really leaky? So one, you do care that this stuff is emitting a signal because you have mutual interference within the box. Many years ago at a radio station I worked at, I worked with very talented individuals who used to design their own circuits and build the circuit boards, and we'd use the equipment in the radio station. And on many occasions, they would design LANs, traces on a circuit board. I'll show you the back of one of these so you can see this for those with the video, the different LANs and stuff that connect the components from point to point. And we actually discovered that certain types, certain lengths, they would actually interfere with the audio. They were making little mixers. And the power supply lines would actually interfere with the audio inputs or outputs because the levels are so low, and they actually emitted a signal. Nobody thought of it. They just thought it was a copper strap, and that was it. That's on a very simple scale, 15, 20 years ago. Now you advance to computers of today, and you're talking 2 gigahertz twice, right? 2 processors in a box, along with how many other processors generating signals to create what you get out of a computer. It's just a nightmare. So testing like we just saw in the video is crucial to prevent interference within the box, with a box next to a box. Say you're in a server room. Can you imagine being in a data center? 37, 40, 50 servers running, and every one of them is leaky. Just picture what would happen. I mean, that's just a simple way of looking at it, but that's what you get. I mean, it's a transmitter.
In just a minute, we're going to hear about some of the practical side of what happens when equipment generates hash, RF interference, stuff that you don't intend for it to generate, and it gets into radio service. But first, I want to, Chris Tarr, give us a little discussion here. Inside anything that is a digital piece of equipment, there are square waves going on. And these square waves can be anywhere from, a few hertz or tens of hertz or thousands of hertz up into the megahertz and gigahertz in terms of how fast the signal, the square wave is changing state. Why is that? Why is a square wave? Why can a square wave be particularly harmful when it comes to generating junk that you don't want?
Well, just because it's constantly switching on and off noisily, I guess is the best way to put it. A square wave generates just a whole lot of noise, and when you have something that is generating a lot of square waves very quickly, or switching on and off, or something like that, it generates a lot of noise. And a great example is, take something like an LCD monitor and take an AM radio up to it and listen to what's going on there, and all you hear is noise. Now, with your portable AM radio, that may not be a major problem. However, if, for example, you're working with a microphone or something like that has a very low line level on it already, or very low powered signal on it already, you could easily see how how that kind of a loud noise, that pulsating square wave noise, how that could quickly overpower a signal from a microphone. All of a sudden now, you get some static and you get some noise on these lines. So, the square waves are very destructive that way, just because of the pulsing nature. And of course, also, again, it's one of those all or nothing type of situations, and can generate a lot of white noise and a lot of harmful interference to things, especially things that make good receivers.
I think one of the interesting things about a square wave, and we used to use square waves a lot to test out analog audio paths and AM transmitters, because if a circuit will pass a square wave, then it probably has pretty good bandwidth. So what's interesting is if you deconstruct a square wave. Of course, square wave, voltage goes up, it switches positive very quickly, goes along for a while, and then switches negatively very quickly, or switches off, depending on how the circuit works. But it's on, off, and the rise time and the fall time, ideally, is very fast. Well, if you take a square wave, and let's say the square wave is 1 kilohertz, okay, to be easy about this. If it's a 1 kilohertz, 1,000 times a second, it goes on and off. It one whole cycle of on and off. Well, it turns out that if you draw this out on graph paper like an oscillogram, you could draw a sine wave, which is a nice pure tone, only takes up one place on a frequency spectra. If you draw a sine wave to kind of fit within the square wave, so it's a 1 kilohertz sine wave, well, great. You have this real nice, pretty 1 kilohertz thing. And if you look at it on a spectrum analyzer, it only pops up at one place at 1 kilohertz. Well, but the problem is if you draw this sine wave that fits inside a square wave, you have a lot of area in the square wave that's left over, that's outside the sine wave. Well, how could we fill that up? Well, what if we double the frequency of the sine wave? So wherever the sine wave goes positive, we go like positive and positive. Okay, so we draw a second harmonic within each square wave block, right? That kind of starts to fill it up. Well, then let's draw a third harmonic in there. So we draw a triple frequency wave in there. We do enough of this, and we start to feel like, hey, these sine waves, when added together, are kind of becoming the square wave. So the point I'm trying to make is, and I hope I'm doing it okay, but a square wave contains a ton of harmonics. The squarer it is, the higher the harmonics are that it has. So a 1 kilohertz sine wave is going to have harmonics at, I probably should have said double. It's going to have harmonics, I believe, at all the odd harmonics, at 3 times and 5 times and 7 times and 9 times the fundamental frequency. And it's going to have a little bit of all that, theoretically infinitely far out, practically not quite infinitely far out, but there's going to be a lot of noise. Also, you can see this on an audio spectrum analyzer. If you're just using some program that shows you an audio spectrum pretty accurately, Cool Edit or Adobe Audition will do this for you. You can play some music that has a lot of harmonics, maybe some distorted trumpet or maybe an electric guitar, and you'll see the fundamental frequency, and then you'll see all these harmonics in there. Not necessarily.
And aside from that, when you're talking about devices that generate several types of square waves, you have the sum and differences of those creating harmonics. So, not only do you have the harmonics of the single square wave, but also if you have things generating various square waves at various frequencies, you have those that can do some mathematical things and create harmonics all over the place. And all of a sudden now, what shouldn't really be matter much in terms of noise is noise all over the place.
So then the next thing that happens is you get computer circuitry, processors, FPGAs, DSP chips in it, and you start operating these things at pretty high frequencies, up in the tens or hundreds of megahertz, or even in the gigahertz area. Well, then the wavelength of a gigahertz signal is pretty short. I'm sorry, I don't know the math right now, but it's shorter than my hand, right? And so any wires that exist on the circuit board, or a flying wire from a circuit board to an input or an output or something, those become antennas at those frequencies, really good antennas. And that we don't want that. That's why there's so much shielding that goes on inside a product that needs to be quiet and has wires in it. And we try to, when they lay out circuit boards. Chris, why don't you show us that circuit board there? I know that the designers at Musicam, just like the guys at Telos, they work pretty hard to get parts close to each other that need to be, to minimize wire or trace length, to minimize the number of antennas they're making. You want to comment on that?
That's absolutely true. It's the design everybody has to follow for anything electronic these days, or in the past. And actually, as you were talking about the harmonics in a square wave, there are the reasons they use square waves for timing is for timing on clock references, because of the speed and the transitions that create the square wave. And also in audio, in the analog to digital, you'll find timing will be in a sine wave, because you don't want that noise when you're dealing with the audio components. Something I was talking with some folks about just the other day with some questions that came up with some of our customers with some wacky, transmitter sites that would have several 100,000 watts of RF. And they're like, we're getting the signals on everything. I'm like, yeah, well, that kind of electricity, you probably got 2 volts per meter in your building. And the guy chuckled and goes, no, it's about 1.5 volts. So, when you're designing stuff, exactly. The environment you're in, the circuit design and this something as simple as 1/32 of an inch on a circuit board is enough to wreak havoc or destroy it, or make it a radio receiver, depending on the size of the circuit and what frequencies it's sensitive to or resonant at.
I was going to ask Tom to describe what happens when all this hash coming out of stuff. If you're a ham radio operator like Tom is very much into, then hey, I've had stuff around my house, a wall wart power supply, just make all kinds of noise on the same frequency as a 2-meter repeater I was interested in listening to, but I couldn't. Now I walk away from the house a couple hundred feet, and I can pick up that repeater just fine. And ended up, pulling out all kinds of stuff in the house to find out where this hash was coming from, and it was some cheap router wall wart. Tom, tell us about RF that gets out of stuff that it's not supposed to get out of, and what does that do for things that you're trying to take care of?
Well, your example with the ham radio is exactly right. I mean, there are certain things I can turn on in the house here and lose part of the 80-meter band, lose part of the 40-meter band, lose part of the 2-meter band, because let's face it, you're trying to receive a signal that's this big, and all of a sudden you're presenting a signal that's this big next to it, and the big signal is going to wipe out the little one. Around the radio station we have problems with that. I mean, let's face it, we're trying to listen to ourselves off the air. We have microwave receivers that you may be at the transmitter site that are picking up our studio signal. We have satellite receivers that are picking up a little teeny tiny signal from the satellite that if you all of a sudden present it with this big burst of noise anywhere near the dish, you're going to lose your satellite signals. And let's take it one step further. Let's look at the medical profession. If you're in a hospital, if you're in an intensive care unit and they're watching you, they're monitoring your heart. I mean, they're looking at teeny, itsy bitsy signals with these wires all over you. You turn on a computer, you turn on a cell phone, you turn on God knows what, and all of a sudden all this hash comes out. I mean, they're not going to know what they're looking at, and the guy dies. So, it's very critical that we know what's coming out of these devices, and we have some way to control it, or at least to know what it is, so we can either notch it or at least be aware, so we know if something happens. In one example, I have a lot of us in radio. We all know Marty transmitters. They're remote pickup transmitters. They're little transmitters that we use to get the signal from a remote broadcast back to the studio. Well, in the days of analog television, those guys used to basically run for the hills if they saw somebody, if they went to a news conference and one of us pulled out a little Yagi antenna at a Marty transmitter, because all they would get would be herringbones all over their video. Instead of good usable stuff. So, it gets into cameras, it gets into the computer monitors, it gets into your television. There's a lot of, and by the way, all these devices can generate RF fields too. So, it could be a big problem, and that's why we need to know what exactly is coming out of it, so we know how to deal with it.
All this digital technology is interesting in that it has the potential to bite us when we're not expecting it. When we as broadcasters were using all kinds of analog gear, especially out in remote trucks and analog microwaves and VHF and UHF stuff to get signals around, we could tell if a problem was creeping in, because you'd hear, I hear a little bit of hash. I see a little bit of a herringbone design on my TV transmission. And we could there were degrees of interference that were fairly linear or maybe fairly logarithmic with the closeness to the proximity or the power of the interfering signal. But now that so much stuff is digital, we've kind of lost sight of hey, this is working, but by how much is it working? It's that digital cliff effect, right? At some point, there'll be enough interference on something to your cell phone or to an ENG transmitter or receiver or a satellite, digital satellite receiver, or even an HD radio. You're listening to your HD radio, those few who are, and it's just fine, and all of a sudden it goes away. Well, it might be the signal level drop from the station, but it also might be some interference from the power lines overhead, a bad insulator somewhere, things that you would have noticed in an analog world that you don't notice or don't immediately recognize the cause of in the digital world. Am I?
Well, especially because especially in the digital world, we're dealing with power levels that are a lot lower than in the analog world, because you don't need to have that high of a power level to decode digital. So what may have worked perfectly well in analog with the noise around it in the past may not work at all once you've moved to digital and have dropped the power level. So that all factors into it as well. Plus, digital's kind of can be a little hard to control inside of certain amounts of bandwidth, and as you know, with HD radio, there's shoulders and cliffs, and the digital world is completely different when it comes to dealing with RF compared to analog, and it requires a lot more. It requires a lot more attention. Is a good way to put it.
Yeah.
You need a very linear space.
Right.
The digital world is very linear, regardless of what you might think.
So, hey, I was talking with one of the design engineers at Telos, a guy named George, and George and I were talking about the proliferation of the number of screws that hold the top on a piece of equipment nowadays in a lot of broadcast gear. And I remember getting audio processors from either Orban or from Omnia or gear from other companies as well, and having moved 28 screws from the top of the thing just to get the top off so I could get inside. And George reminded me about why this is important, because, you know, whatever the space is between two screws, between, you know, the lid and the you know, the sides that are turned over on a piece of gear, you know, that's not a solid connection between the screws. The connection is only solid at the screws. It only takes, you know, a particle of air spacing between the top and the bottom to make a resonant circuit between the top and you know, the sides that it's supposed to be touching. That's why some gear has finger stock all the way around, you know, to keep some pressure and try to hold everything in. But this is why, if you ever complain about the number of screws on a piece of gear, it's because some designers, you know, they weren't trying to spend more money on screws. They were trying to keep, first of all, EM, you know, radiation from getting out, electromagnetic radiation from getting out, and a lot of times these are going at a transmitter site with a lot of high power FM going on, maybe an HPA, a high power amplifier for a satellite uplink that's in the gigahertz range. Maybe it's at an AM transmitter site with, yes, very long wavelength, but also could be, you know, 20 volts per meter of signal strength right there. Guys, have you ever cursed a piece of gear because it had too many screws in it?
All the time.
Oh, I've cursed
all the time.
Yeah. Who hasn't?
Oh, yeah.
But I once had sorry, Tom.
No. Go ahead, Chris.
I have to say that the screws definitely played a role in one of the jobs I had many years ago. I was at a transmitter site. It was an exciter. Exciter required, I think, it was about 12 or 15 screws to secure the top. It was an older type, not a fully synthesized. So if you needed to change frequencies or make adjustments, you had to pop the cover and go inside. So the previous person at the site decided, you know what? I don't need to put all 15 or 20 of them screws back in. We're just going to do like the corners, you know, four screws. That's it. Well, it was interesting. It was an AM/FM combo site. It was an AM, high-powered AM, 50 kilowatts, directional, and you know, transmitter building is sort of smack in the main pattern. And every so often, you get a phone call from the FM folks saying, you know, I think I hear something really low in between the songs. And I'm like, what? And you listen on the air and everything's fine. Like, well, I can't hear it really because we're playing top 40 and we're doing, you know, very you know, artistically processed audio. So the noise floor may be 10 dB. Anyway, going through, so one time I said, all right, fine. Well, overnight on a weekend, we're going to go off the air for about an hour and do some measurements, do STLs a little bit. And believe it or not, we heard nothing. So the AM station was a daytime only. So we decided to turn the AM on, and lo and behold, down in the noise, just I shouldn't say in the noise, but above the noise floor, there's the AM signal. You can hear the tones. I was doing a multi-tone. Turns out that the cover on the exciter, because it wasn't properly RF tight, was getting AM leakage, and somewhere in the circuit design, somewhere in the exciter, the AM would travel along the wires and make its way into the modulator and become part of the FM signal. And that was the one time I was like, okay, from now on, 27 screws or 6 screws, they're all going back in. And I'm going to make sure they're nice and tight.
We had to change a hard drive in a BE HD exporter, and sure enough,
gosh.
you know, there's about 800 screws on there, but you know, it makes sense because, again, those go at transmitter sites where there's going to be a lot of RF. But I'll tell you, you know, one of the things, not on this particular piece of equipment, but on any piece of equipment that has a ton of screws, it always seems like, and it's a Murphy's Law thing, that the screw heads get torqued out, no matter what you're doing. You know? I mean, they could have, you know, the biggest, you know, the nicest screws on the planet, but eventually one or two of them will get stripped and you can't get it out. And you know, you've gotten 15 screws out and the 16th is stripped out, and you're gonna, you know, you have to drill it out or cut it or, you know, something like that. Always happens. It's one of those Murphy's Law things.
You know, I once had a general manager, after watching me remove the cover from an STL receiver, look at me and say, "Why don't you go down to the hardware store and get a screw gun?" I mean, even he got it.
Here's Kirk Harnack's words of wisdom and tip, and you guys may all already do this, but for years in my contract engineering business, it seems like I was stripping out Phillips head screws. You know, I mean, you'd really have to push hard and turn in order to not strip the screw head. And a guy that worked for me was Robert Benjamin, who used to work with me in Harnack Engineering. He said, "You know what we need to do, Kirk? we need to get some actual real Phillips head screwdrivers that meet the spec, because 99.9% of all the screwdrivers that are supposedly Phillips head aren't. They really aren't made right. Really? Yeah. So it turned out I was ordering some parts from Otari. Remember Otari? You have to order some heads and brake bands and things. I was talking to Otari, and one of the parts sellers said, "Hey, by the way, we have a screwdriver set on sale, and by the way, it's the real thing. These are really good Phillips head screwdrivers. You won't strip screws out." That's funny. Robert was talking to me about this just a couple days ago. So I ordered that. So I got this Otari set of screwdrivers. I think it was just two different sizes, like a number 1 and a number 2 size Phillips head screwdriver. I never stripped a screw again. I mean, of one that was these screwdrivers were meant to fit. They would turn anything. There was absolutely no wobble, no play, no wallering about. Just put the screwdriver in and just give it a turn, and it would turn any screw. It's just amazing. You guys ever experienced that? Am I off in left field here?
Not at all. No, I've had the same experience. I had a set of screwdrivers that I used to use and cherished and fought people with all the time. And I learned early on the same thing. When I would put a Phillips screwdriver in, like, wow, this has got a lot of play. And I did some research, and I said, oh, I'm using the wrong size screws, number 1, number 2, number 3, depending on what you're doing, and whether it's metric or imperial. And, boy, I'll tell you, what a difference. You're absolutely right. If you have the right size, the right fit, the glove fits.
You mean to tell me they actually make screwdrivers that have the little plus head on them? All this time, I've been just taking the flathead and turning the Phillips screw. Oh, see, now that's what I've been doing wrong.
Well,
I learn something new every day.
I was reading something recently about somebody was complaining they had some radio or something from Japan, and they could never get the screws out without stripping them, and they bought the best screwdrivers and such. And apparently there's different standards, because the Japanese have a slightly different standard for the what looks like a Phillips head screw, but it's not really a Phillips head screw.
Well, that may have been the Otari thing, because it sure fit Otari screws, and it fit Phillips-looking head screws, crossed screws, and it fit everything else that I was working on. But I wasn't working on deck screws.
And seriously though, I did invest in, I don't remember the manufacturer now, but actually a set of small to large true Phillips head screwdrivers. And you're right, Kirk. I mean, when you do that and you can actually get the exact size for the job, it works perfectly. I don't have very, very rarely do I have an issue getting a Phillips head screw out of a piece of equipment when you're using the right screwdriver. But so many guys have 1 or 2 or 3 screwdrivers tossed in the toolbox. It's literally a set of like 10 different size screwdrivers, and it's a right tool for the job kind of thing.
I guess the easy test is if you have to turn a Phillips screw, like there's 28 of them on the top of some piece of gear you're trying to open up. If you put whatever screwdriver you have into the screw head, and there's any play at all that you can feel, it's not the right screwdriver. I mean, it may be look like it's the right size, but it's not cut the same way that screw is. Of course, that's also assuming that the screw head itself is formed, cut, forged, whatever they do, correctly, and it may not be either. So, I mean, it certainly could be the screw, but on quality gear, they're going to use screws that are actually right, and it does make a difference. We were talking about stripping those out and not being able to put them all back in. And I was going to mention that just because there's an area between 2 screws on the lid of a piece of gear, now that doesn't mean that there's room there for a signal to like leak in or leak out. That's kind of not what I'm saying, but there is room for that area to be resonant, and so you would get like a tuning fork effect. You would get external signal resonating that parallel circuit, and then that parallel circuit re-resonating it back into the piece of gear. At least I think that's how it works. Any different ideas?
That's true. That's part of it. No, that's true. You get skin effect and a little oxidation between the surfaces, and you create a capacitor or resonant circuit, and before you know it, you've got all kinds of things going on. So anyone who's worked in an AM facility knows.
It makes circuit boards, Chris Tobin, like the one that you're holding up there. That's probably a multi-layer board, and probably one of those layers has got a very specifically designed ground plane on it to cut down on radio. Not only to provide a good circuit ground, and probably it's got separate grounds for the audio portions and the logic portions of that, and maybe even a third ground as well. But they'll take those grounds, they'll divide them up, and they'll make the planes, just as big as they can, because they act as shielding.
Yep, absolutely. And matter of fact, on this particular board, there are 5 different binding posts for grounds for test equipment, for the automatic testing, the ATE. And I was asking about, said, is it that critical? And one of the guys said, he goes, I can show you on a scope what it looks like at this particular part of the circuit board. If I move the ground only 1 inch in one direction, you'll see a difference. And we looked at them like, whoa. And they have ground points in strategic locations around the processors in order to get the proper measurements. Just sort of like that chamber, that RF chamber for testing the equipment for the console with the antenna.
One of the concepts that's kind of interesting about digital circuits, you think, well, a digital circuit ought to be a pretty assured thing, right? It's not like an analog circuit where you got this balancing act going on all the time. Well, actually, designing digital gear and getting, this IC to talk with this FPGA, to talk with this CPU, to talk to this RAM, to talk to this DSP chip, there's a lot of room for things to not talk to each other real well. And the job of circuit designers and physical layout designers is to make sure that these things will talk to each other without being just quite on the hairy edge of not talking to each other. And it's quite a science that goes into designing this kind of stuff. There's a lot of failure rate with folks who are early at or new at designing digital circuits. It's not just you hook this input up to this output and it's going to be okay. There's a lot involved. If you look at the circuit traces on a circuit board, you'll see so many of them that are parallel and they take turns here and there. And that's not just to get the signal from here to there in a pretty way, or just to get it from one place to another. A lot of those are designed really specifically so that chips will talk to each other as error-free as possible. Hey, I want to remind you that you're listening or watching This Week in Radio Tech, our weekly podcast about broadcast, radio engineering, audio, RF technology. Today we're kind of talking about some design factors. We looked at a video earlier in the show, if you want to rewind and go back, about electromagnetic testing of gear. We looked at an electromagnetic testing lab. With me on the show are Chris Tobin from New York City. Also with me are, there he is, and Chris Tarr from Muckwonago, Wisconsin, and Tom Ray from the Hudson Valley of New York. We're going to roll right along here in a minute. First, I want to tell you about our sponsor, which is Axia Audio. Very glad and happy that Axia is a sponsor. They're also my employer, so I appreciate that very much. Let's take a look at the first page of the Axia Audio website, if Burke happens to have that ready for us. I want to point out of really interesting news items that have occurred just here in the last few days, last couple of weeks. Under the news section, scroll down just a tad there, Burke. One news story is that Orban partners with Axia Audio. And just below that, Studer has become an Axia Audio partner. Now, that's pretty interesting. Orban, of course, is friendly guys, but they're a competitor to one of our divisions, Omnia Audio. And Studer makes audio consoles. Well, they're kind of a direct competitor, too, to the Axia console line. Why would they partner with Axia? Well, the reason is the technology behind Axia consoles, and that's LiveWire. LiveWire is not so much something that the folks at Axia invented, but they figured out ways to take a lot of existing protocols and add just a little bit of timing magic to that. And what they come up with is a way to send unbuffered, linear, that is uncompressed, digital audio over Ethernet networks, Cat5, Cat6 cables, using good quality switches like Cisco switches. And before LiveWire came along, this really wasn't possible to do with low latency. Other technologies like CobraNet and EtherSound, these work great for what they're intended for, not so great for a really low latency and totally routable technology for audio like you need in a broadcast facility. So I'm in Riga, Latvia right now. Riga, at the University of Riga, is where the whole idea of LiveWire was proved out. Large simulations were done, and they just have an amazing facility. I was there today meeting with a fellow named Gintz Linus and also Normans and their staff, where they really pound on ideas, technologies and equipment to see whether or not they're going to work well or not. See if there's possibility or hope in some emerging technology. So about 8 or 9 years ago, right here in Riga, is where the concept of routable, unbuffered IP audio was proven out. And what does LiveWire let us do? Well, it lets us route audio over Ethernet switches that are far less expensive and not proprietary like we in broadcasting for decades before, and that was using proprietary TDM, or time-domain multiplex audio routing switches. Very expensive, very few of them made, and if we could get rid of those, if we could go to a technology where we get to use off-the-shelf Cisco or HP Ethernet switches to route this heavy-duty, unbuffered linear audio, well, that would be quite a favor to the broadcast industry, and that's what LiveWire was all about. So if you get a chance, check out the website, axiaaudio.com. There's a page with and news releases. And why don't you check out and read about why the folks at Orban and the folks at Studer decided to partner with Axia's LiveWire technology and put it into their own products so they could connect more easily and conveniently to lots of other broadcast systems. 2,500 Axia consoles on the air around the world right now. Thanks, Axia, for your support of This Week in Radio Tech. All right, gentlemen, we're talking to Chris Tobin, Chris Tarr, and also Tom Ray on This Week in Radio Tech. And
wait a minute, you said gentlemen.
Yeah, well, okay. I don't want to hit the disclaimer every time, Tom. I guess I'm kind of done with the subject of electromagnetic radiation, at least from the notion of it coming out of pieces of gear. And perhaps interfering with other stuff. By the way, the video that we saw earlier, where we saw some spikes of energy above the horizontal red line, that's the can't go over line. Actually, that's the can't go over line for one class of certification. The gear that we were testing actually met a looser classification. But what was interesting about the testing that we did today in that chamber was we weren't testing for final certification. We were testing to find out where we now need to go pay attention to knocking down any radiated signal. And I asked the director of the testing program, I asked him, hey, it's expensive to test in this lab. I mean, they charge a couple $100 per hour for time in that lab. Do companies ever come in here with a lot of bravado thinking, oh, our product is great, we tested ourselves, now we got to get a certification, so we need a certified lab. Just go ahead and run the test. We think it'll be okay. So they go ahead and run the whole day test, the test for everything, and in 10 minutes, it's already busted some test. It's really, really stringent. So I just wanted to point out that today we were testing not to get the certification, but we were testing just to find out, okay, where do we need to pay attention to right now?
Hey, Kirk, got a question for you. When they were probing with the high voltage probe, were they looking specifically for a breakdown voltage on the switches, or were they trying to simulate a static shock?
That's a great question. I think they were really trying to simulate the mother of all static shocks. You walk across 15 lambs and a wool carpet and comb your hair twice and hold a balloon and touch the console. And they wanted to make sure that the console, wouldn't do something stupid, or whatever piece of equipment it is, wouldn't do something stupid or wink out or lock up because of that. So there were two tests: a 4 kilovolt test where they touch just every piece of metal that they can find. They hit it with 4 kilovolts. I don't know how much, how many joules or of power are behind that. It's a battery-operated device. It's got a whole bunch of batteries in it, so it's kind of like a stun gun. But it's calibrated in terms of its voltage. So it's not like taking 4 kilovolt feeder circuit and blowing the thing up. That's not the current's not important. It's the the EMP that's going on right there. Then when they took the 10 kilovolt charge, the idea was to touch every piece of plastic, every button, every lens over some display, every knob, and see if that made it do anything. It's of course it should be an insulative surface, being a button or a knob or a lens, and it's it's just to see if anything goes wrong under those conditions.
Interesting, very interesting.
too. And they have very specific criteria written out from the European Union as to what it has to pass in order to get the CE certification.
Well, when they do that, Kirk, would they also maybe do that while they're measuring for RF emissions from the thing to see if anything changes once they hit it with a static shock?
No, that's not part of the protocol, and that would be really difficult to do because you'd have to do the stun in the same room as in the Faraday cage room, and I don't think that'd be very very possible or convenient to do.
Yeah.
One thing I did notice,
it wouldn't go well.
Yeah, it'd make all kinds of noise on. Part of that video, when they had the equipment sitting on styrofoam blocks, the top of the table was a big ground surface. That was absolutely, well, it was their local ground surface. So everything was tied to a big stud at the corner of the tabletop. Was the metal part was probably almost a 1/4 inch thick. And then the high voltage tester was tied to that as well, one end of it, and then the other end is what they were poking on the piece of equipment. I asked them, "You guys ever shocked yourself on this?" They said, "Oh yeah." Hey, I tell you what, before our hour slips away, we've got another video to take a look at. This one's kind of fun. Not so serious as EM testing, although that's interesting. We've got a video here. I got to visit another radio station in Riga. Riga's a happening place, and you'll see here in just a minute. I'll shut up and let's roll the video. Oh, not bad. Let's do a moment of programming in Latvian language, and while we look at the control room.
Ierakstus un padomā, kam tu velti ikdienu? Savu vai svešu sapņu piepildīšanai? Žurnāls Annas psiholoģija. Jautājumu un atbildes par to, kā iepazīt sevi un dzīvot labāk. Jaunajā numurā lasi. Šoreiz atklāt par mīlestību, nevis seksu. Kā saprast ķermeni un pārvarēt bailes runāt svešvalodā?
I have no idea, but it sounds good. So this is the control room of one their most popular station. They have 3 or 4 stations at Radio SVA. This one has a split audio console. It happens to be an Axia IQ console. There's the OLED metering going on there, and the clock and the timer. The station has a really active morning show. The morning disc jockey, very popular guy, has been around for quite a few years in Riga, Latvia. There's the left-hand side of the console, and there's the microphones, 1 input, and mic 2 and mic 3. They have, I guess, about 4 or 5 people on the morning show. This is the right-hand side of the console, where they have a few other inputs, and the telephone control is on that side. There's telephones. There's the phone lines. They're all idle right now. Nobody's calling in. This was really interesting. They do a live web stream, video streaming as well, and they do automatic switching of these webcams. Whoever's mic is hot, whoever's mic has got some audio on it, they have a computer that switches to that mic. It also delays the video and audio such that it looks like there's a director switching the show in anticipation of whoever's going to talk. It's just amazing. It's running on a Linux computer. It's proprietary software. I don't know that it's available commercially. This is the production studio. Made a quick tour in there. It's really fancy. It's for music production as well as voice tracking. It's got a big Mackie audio console in there, a lot of multi-track recordings, some keyboards. Oh, and a mini Moog synthesizer in there as well as some other keyboards. And in the performance area, look, there's a Hammond organ in there, as well as the Leslie speaker that goes along with it, and some Neumann mics there on the side. This is the main Neumann mic where the vocal talent would stand and read their copy or perform or sing. Behind the vocal talent, there's this really interesting bar that's kind of up about head level, and it has a bunch of headphone jacks on it. So talent, a number of talent, 8 people can all have their headphones on and not be tripping over their cords because they're suspended up in the air. Looking around the station, here was a satchel that had a radio motif on it. That was kind of cool. I don't know where I could get one of those, but that looked pretty interesting. Every radio station has bumper stickers and posters on the wall, especially a rock station like this one. Their rock station apparently hosted Metallica. It says Paldies across there. It means thank you in Latvian. This was their tour from 2010. This was Rammstein made an appearance at the Riga Arena in 2010. They all came by. Paul D's there. Yes, thank you. And signed that. Lenny Kravitz also came along. And this must have been their 2010 wall with his black and white Latvia on 11-11-11 tour. Lenny came in and signed that. There's the door to the technical office. We didn't go in there, not a lot to see, just a bunch of manuals and some soldering irons. So there's our quick tour of Radio SVH in Riga, Latvia. If you ever go, a lot of good radio going on in Latvia, so check it out.
All right. One thing that it was so exciting to go to, and I have gotten to travel around the world and see radio stations in a lot of other countries, and in a lot of countries, it still feels like radio did in the U.S. in the 1980s. Now, there's a lot of passion going on for what they do, and yes, they're automated at so many stations. You thought the control room we were in, there was nobody in there, right? The morning show was over, and so they were out of there, and they were automated. They're using an RCS automation. Somebody in the chat room asked which automation. It was an RCS, and they had Selector running on another computer right there. But there was so much passion for what they do, and they still make lots of appearances, and they just have a good time with a good-sized staff. It kind of makes me yearn for those days. And not everybody in the U.S. has gotten away from that, but it seems like so many stations have. Any questions about the video that we just saw?
Hey, in Latvia, what type of regulations do the broadcasters in that region need to follow, or how do they enforce, or I guess the equivalent to say the CRTC in Canada or the FCC here? What do they do over there?
That's a great question. I don't know much about that. Things seem, there don't seem to be too many pirates on the air. Latvia is a small country in terms of population. Riga is about 1 million people, so it's about the size of Nashville, where I live. And the whole country is just a hair over 2 million people. So, it's just not a lot of population. I have noticed that there does seem to be a lot of foreign ownership, complete ownership of some of the broadcasters here. So I've been to some stations on my last trip here that were wholly owned by Russian companies, and they were Russian-speaking radio stations. Half the population here, approximately, speaks Russian and might prefer to speak Russian, and the other half are the people who were natively here or descendants of them who prefer to speak Latvian and maybe not be so crazy about speaking Russian. Due to the Russians taking the place over for some decades. By the way, we were talking earlier about language. I mentioned that, hey, these guys at the lab, most of them spoke English, and I was curious about this. Why do so many people in Latvia speak English? Well, they need a common language to do business with all the countries around them. With Finland and Sweden and Poland and Germany and Lithuania and Estonia, if they trade with them, They don't Russian. Well, they don't really want to speak Russian. A lot of them don't, and so what else are they going to speak to have a common language amongst all these different countries in the area? It turns out to be English for a whole lot of things. The stations that I was at today, the SVH or SWH, as we would say, they're I believe wholly owned out of Ireland. So I don't think that I didn't hear about any local ownership of those stations, but there are some stations that are locally owned. There was kind of some guy. It must not be horribly hard to get a license, because there were some guys I heard about who they didn't like a corporatizing of the station that they were at. They were real creative guys, and so they quit, and somehow they obtained a legal license, and they just went on the air within the last year here in Riga. We listened to the station for just a few minutes. They do seem to be very they respect the law. Okay, so whatever commission a city of or a country of this size has to put together some laws to regulate broadcasting, apparently it's working okay.
Do they Kirk have do they run the stations at significantly reduced power from what we're used to, or do they actually run stations multiple kilowatts like we do here in the States?
These FMs, I think, had ERPs, effective radiated power, in the neighborhood of 10 kilowatts. Some may be 5, some 10. There's probably a couple that are less than that. And I don't know that the antennas here are all circularly polarized like is so common in the U.S. You know, in a lot of other countries, circular polarization just looks like a waste to them. And so a lot of countries transmit horizontal only, maybe a few places. But I don't know which it is here. I didn't go to the transmitter site.
Yeah, I was just curious because over in Europe you find a lot of stations they run a couple of 100 watts instead of a couple of kilowatts like we do, and they cover a much smaller area but have more radio stations.
Yes, when I was in France some years ago, they have big, reasonably high power on top of the Eiffel Tower, 10 kilowatt, maybe 20 kilowatt. They don't have 100 kilowatt there in France, but they had 1 kilowatt sized outlets in every town. So we were doing some work just south of Paris in Orléans, and so we were in all these little towns like Pithiviers and Le Mans, where they run the Le Mans race. In fact, I had to fix an old Italian transmitter in Le Mans, and I didn't have a manual, and so I tore the thing apart and kind of figured out what was wrong with it, put it back together, I told the guys with me, I said, I need a paper clip and I need a big soldering iron. It's real.
No chewing gum? Come on.
No chewing gum. It was so funny is I got done fixing it, and I was really surprised that my fix worked. Okay. I was just as surprised as they were. Okay. And we turned the thing on, and the meters on this it was an old Italian transmitter. It was an early solid state one. So it wasn't like, decades old. It was, 15 years old at the time, and a solid state FM transmitter. And the meters went, so hey, wow, great. It's working. My French friend said, you are MacGyver. You are MacGyver. No, I was lucky. That's what I was. Oh, jeez.
And you stepped back into the Stargate, and home you were.
But I don't know if these guys here in Latvia have lower power transmitters out in the rural areas, but I kind of don't think so. I was really impressed, though. The technology that they're using, and the the way they keep their shop, and just the way things look. It doesn't feel so different than American broadcasting. You saw the room with the webcams. Well, I mean, we're doing that at our little station in American Samoa, except we hire a Samoan to come in the morning and switch cameras. I got to tell you, the technology of that switcher was really cool. You heard me say it delays the audio and video so that the switch occurs before the loud audio comes in from whatever dude is talking, right? So it's just on the air, on the web stream, the video web stream. It's amazing because the camera switches and then the guy starts talking as if there's a director anticipating who's going to talk. Chris Tobin, when you were at CBS Radio, how did switching work there? Did you have a person pushing buttons?
Yes.
On camera?
Yeah. The production was done manually, in part because of the complexity of the show and the things we were doing. There was talk of looking at some software that would do it automatically, but the shows that we were doing with cameras were just too much moving around, too much talking, fast shooting. And when we did talk to some folks who had software that could do this, they looked at us and like, that's you guys are too fast paced. It's not going to work. And we tried once a couple of years ago. Yeah, even with the delays and the attempts to try and delay and match everything up, it fell apart. So we were still manual. But I think in an FM studio probably, or if your talk format is not a high energy type and it's pretty straightforward, one to the other and back and forth, there's a certain rhythm. So like say like an Imus in the morning show type of format, you could probably make it work automatically.
Yeah. So I don't know what happens when two people talk at once, or if it's a big melee. It did have, it had a default that it would switch to, which was just the station logo. As an engineer, I mean, I'm terrifically interested in, a lot of stations want to do a video web stream, right? And I'm interested in making that happen without having to put more bodies in there to make it happen, to have it switch to whoever's talking. But do so in a meaningful way that usually looks okay. Chris Todd,
Oh. I was going to say, I saw a webcast of a radio station. What they did was one camera was head on to the host, co-host of the show, and then they had a point of view, like a wide shot of the studio, the guest position. So when people started talking, just a wide shot would open up and you could see the guest and talking, and you didn't feel out of place, but that was their way of, I guess, avoiding, manning a complete camera control. I think it was actually the morning host would just flip the button, switch back and forth.
Chris Starr, you guys in Milwaukee, you doing any video web streaming?
Nothing like that. We're just, single camera pointed at whoever's on the air, but that's about it.
Right? Does WOR do any of this?
Not like that, and we don't really do any video streaming. We've talked about it, but if I could find a source for software that did something like that, it might help. It might really help, and it might be a reality. I like that.
Well, somebody in the chat room said, "Well, there's going to have to be a formal gap between people speaking." Actually, not. It's just on the software that I saw. Next to every preview picture coming from. By the way, the webcams were just USB webcams. They had them running. I don't know, probably upwards of 5 to 7 meters or so on the cable, and they seemed to work fine. And then they had to run an audio split from each mic associated with each webcam into an audio board on this computer, which I think may have been a custom-made board that accepted up to 5 or 6 mic or maybe line level inputs. And then in the software you'd associate, okay, this mic is with this cam, this mic is with this cam, and they played with the software enough and got the timing down well, so that if we're talking here and then if Chris Tarr starts talking, bam, it switches to Chris Tarr, but it's delayed the audio and video enough to where it's got time to have a little bit of, I guess you might call it hysteresis in its decision making, so that Chris started talking and he's been talking now for a quarter of a second or a half a second. He's probably going to keep talking. So now I'm going to go back in time to where he started talking and line that up with the video and switch the video right there. That's what's going on.
That's pretty cool software. I mean, that's not available commercially. They should consider it. I think I know of at least 1, 2, 3, 4, at least 5 places I could definitely use that type of software.
I think of 500 stations in the U.S. that would like to have software like that.
Oh, that too. Yeah, that too.
Oh, well, I'll do a little more investigation, but I was told it was proprietary. But I took a photo. I found a quick start guide for the software, so I took a photo of that and got the company's name and all that. But, oh, well, we'll see. Hey, we're kind of rambling on here. Unfortunately, we're out of time. So much for my adventure in Riga. Hey, let's give a quick round for any closing comments. Chris Tarr, you got any closing comments on the things that we talked about tonight?
Got nothing. Other than I someday I do want to hear the story of what you fixed with the paperclip. I'm a little more interested in what that actually accomplished.
Contrary to what the chat room is saying right now, I did not replace a fuse with a paperclip. Yeah, so it was a safe repair. Hey, Tom, you piped in there. Any comments on the technologies we've talked about tonight?
No, I just found the testing interesting, and I really wish I still had a 2 transmitter at WR, because I'd ask you to bring one of those over there, and we could hit it with 17 kilovolts, just for fun.
There you go. And Chris Tobin, thanks for being with us. Any last closing comments?
Well, just I can say all of the years that I've had consoles and static electricity issues, I would say maintain good relative humidity in the studio. Find a way to keep grounding in a proper place, and when you work on sensitive equipment, like circuit boards like these, make sure you're wearing your ESD bracelet and have some fun doing it.
You mean like you're doing right now? Wearing your ESD bracelet?
Yes, thank God. Good thing this is just a prototype.
Hey, I've always wondered about ESD bracelets. Is there a chance of getting extra shocked because you're somewhat grounded, or is there some resistance to ground that's enough to not stop your heart if you are shocked?
They usually put a meg ohm in there, or a little more. So,
well, how fast will it allow you to bleed off any static charge you might have? Isn't that kind of too slow for the purpose?
No?
At those voltage levels, probably not.
Okay. Well, I don't know. I've always wondered about that. Do I really want to wear that? Maybe the one I have didn't have a resistor with it. Maybe I really was well grounded. That would be dangerous. I wouldn't want to do that. Hey, guys, thanks for being with us. Burke, thanks for switching the show. We appreciate you. We do need a show title, so we'll watch the chat room for the next few minutes to see if we can get a show title out of this. Maybe the show after the show we'll pick it out. Hey, thanks to Axia Audio for sponsoring the program tonight. We appreciate that very, very much. Check them out on the web at axiaaudio.com. Thanks to the chat room for your comments and suggestions. And we're going to see you next week on This Week in Radio Tech. Bye-bye, everybody.